we did method of joints for trusses. And this week, we want to finish up with trusses. And this is going to be on the midterm. So everything up to and including today will be on the midterm. So in the seminar today, we want to have an overview of everything we want to cover in the midterm. All right. So next week, midterm is 8 o'clock in the morning here, and we have until 10:15 or so before the next class comes in, so 2 hours, and I'm thinking it's probably going to be about 5 problems. All right. There should be no surprises, but it is on the material that we're covering. So last week we did this truss analysis using method of joints, and what we did was we found the reactions, and then move from joint to joint to joint, balancing the joint in equilibrium, and then solving for the unknowns and getting the forces that we want at each location. So that requires you to think about the reaction, the members coming in to the node, whether it's in compression or tension, and balancing it like we've been doing in all the other equilibrium problems. So now this is a technique called method of sections, and to a certain degree we've done this also, maybe not as explicit, but we've done this system, or we've done a method of sections type analysis before. What we want to do is take apart the truss and look at the forces internally, and we want to balance it in equilibrium again. So in the method of joints, we look at a joint and we balance. We take a free body diagram and we balance it, and we care about the components coming into the node. So the diagonal member, in this case, we get a component, another component, and we balance it, and we figure out and we solve for the unknowns. In this case, method of section, it's exactly what it sounds like. We want to take a section through the truss and solve for the unknown. So in this case, we can jump around. We don't have to stay at one particular joint and then move to another joint and move to another joint. But there is a system to it as well. So in trying to calculate these internal members, we can isolate it. So say I wanted to calculate BC or BE, I can go to that joint specifically, or that member specifically, and I could break it and then balance it. So let's see, what do I want to solve for? Let's solve for BE. Okay, so this diagonal here, by method of joints, we found it out to be 288.7. So I can take any section I want. So I imagine cutting through the member or the structure. So if I cut through, what happens? I'm cutting through this member, and this member. And by doing that, you want to think of exposing the forces, right, in that member. So let's write this again. We do a free body diagram. And we can draw what that looks like. So this is the cut. So I'm assuming we found the reactions, right? Same way we did it the first time. I take this portion of the truss and I imagine cutting through the members and exposing the forces. So I want to cut through BC and show a force. Cut through BE, show a force. Cut through AE and show the internal force. So I don't know what those forces are at this point, but I know that these two members connect to point E, over here. This member is connected to point C over there. But I can now isolate particular forces, and using equation of statics, I can solve for the particular unknown that I'm looking for. So in this problem, what do you say? This is 60 degrees. This becomes 30 degrees, right? So if I want to balance this system, how can I do this? Using equations of statics, some of the forces in the x have to be equal to 0, some of the forces in the y equal to 0, some of the moments have to be equal to 0. So think of that as just an equilibrium problem. If it was a blob in space, and I had that, and that going on, it's the same thing, right? We would resolve those forces in some manner and balance this thing. I care about the components in this direction, care about the components in this direction, and I can normalize everything, I can balance it. It's the same thing here. I can look at some of the forces in the vertical direction, and I can imagine or look at this diagonal. It's the only vector I have that has two components, right? So if I take the components, I end up with something like that. Then I can add all my vectors. I can add all my vectors in the y direction, all my vectors in the x direction. So what are the vectors in the y direction for this problem?
250, and then the y component of point B.
Okay, right. So 250, let's call it positive going up, 250 pounds. The vertical component of BE, okay, so going down, so it's minus, so PE sine 30. Okay, equal to 0. So I have one unknown and I can solve for PE. What's my, oh, I'm sorry, cosine 30, sorry. So PE is what? 250, right? Put on the other side, 250 divided by cosine 30. What do you get? 288.7 pounds. And it's going away from the node. So is it compression or tension? Tension. And that's what we end up with method of joints doing the same thing, right? Okay, so I did it in a different manner, but I really did the same thing. All I did is I just balanced the system, right? So it's up to you then to, now you have a new way of thinking of the structure. You can quickly isolate something, find that internal force, and quickly zoom in on it. In this case, we had to go point to point to point, and we had to travel through the truss. In this method, I can isolate and find one particular member if that's what I'm looking for. Let's do, how do we find, all right, how would I do AE with this model? I'm looking for AE, I'm looking for this member here, and I've already cut through that member, so I'm looking for this force, right? How do I do it? If I was to do some of the forces in the horizontal direction or in the x direction, what happens? What?
You have two unknowns.
You have two unknowns. And I could do that, but then I need an expression, another expression, right? So how would I do it? How would I do it using moments?
Moments at A.
Okay, so if I put moments at A, AE is going through A, so I can't find out what it is. But where else could I do a moment?
B.
How about B? Why B? I put myself at B, this vector goes away, this vector goes away, because it goes through me. And why does it go away? Because the moment arm is 0. So I don't have a moment around B. So then I'm faced with just this force and this force. So with two forces and a distance, I can figure out what AE is. But I need this distance. What is that distance based on this triangle? This is, I think we said this is 10 feet. Yeah, 10 feet. So what's this? What's the length?
Do the area triangle.
You can do, not the area, but you can do Pythagorean theorem, right? So if this is 10, 60, 60, 60, and this is 10, right? What's that? What?
14.1.
What?
14.1.
The other way. What?
8.6.
Yes, 8.66. You're just doing it the other way. Yeah, 8.66 feet, exactly. So, taking the moment around on this structure somewhere to my advantage, I'm trying to locate, put myself somewhere on this structure to eliminate unknowns. So I put myself at B. So if I sum the forces or the moments about B, I know they have to be equal to 0. I'm going to say everything going clockwise is positive. So what happens? What's the 250? Which way is the 250 spinning around B? What? Clockwise. So it's positive. So 250 pounds times what? What's the distance?
Negative 5.
What?
Negative 5.
Well, it's 5, but it wouldn't be negative. It's spinning this way, right? This force is going like that. So this is 5 feet because the triangle is 10, right? And that's half the distance. So it's 250 times 5. What else? What's the AE term doing? Which way is it spinning? Negative, right? It's going this way. So it's minus AE times what? 8.66. Is equal to 0, and AE is what? Yeah. 144.34 pounds. Is it compression or tension? It's pulling on this node this way. Yeah, it's tension. All right, that's what we got here. So that checked out, right? What else do we need to find? Okay, so we found BE, we found AE. How do we find BC? What?
Some of the moments in the X.
Some of the moments.
No, sorry, some of the forces.
Okay, so if I sum the forces in the X, okay, so then what happens? I end up with, yeah, you can do it this way. I have a force which I know. I take these components, then I have this unknown, this which I know, and then I have that I can solve for it. could definitely do that. How about with a moment equation? How would I do it with a moment equation? And I don't care, on a test, on an exam, or a question, you could do it any way you want. But there's always more than one way of doing it. Right?
Do the moment of point B.
Yeah, so what does that do for me? That makes my life a little bit easier, right? If I put myself at E, I take this force out of the equation, I take this diagonal force out of the equation, I'm just left with this and this again. So I can solve for BC. That might be easier than balancing everything in the x direction by taking a component. I mean, you can do that, that's fine, and it would work and get the answer. But let's take moments about E. And we're looking for BC. So summing moments about E give me this 250 spinning this way and this BC spinning this way. So what is it? 250 times what? What else? And BC, is that positive or negative? Positive BC times what?
Is it 8.6?
Yep. Is equal to 0, and what happens? What's BC? Becomes a negative, what?
288.6.
Yeah, I have 288.7 pounds. So, because it's negative, what's the deal? What's going on? Right, it means that this direction is not right. This direction is going the other way, which does what? So it's in compression. So BC is equal to 288.7 pounds in compression. And that's what we got here, we met the joints, so that makes sense, right? So it didn't really matter, again, the vector direction didn't matter for us. Once we knew what was going on, we can change it, right? We knew it was, I picked the wrong direction for the problem, but the negative sign appeared and told me that it was going the other way. So that's all I care about. So, excuse me. So with that, it's pretty powerful in the sense that I can jump through the structure. With a little structure like this, it may not make a lot of sense. If I have to analyze every single member to design it, then I'm probably going to do it one of two ways, or I'll do whatever's convenient. But on large structures, on bigger structures, method of joints becomes more cumbersome. So let's look at another problem. So I've got this truss system. This particular configuration is actually a known truss called a Baltimore truss. They can find a lot of different bridges. May have this configuration, and the small little links help the bracing of the long diagonals. So It cuts down the brace length. So if I have this structure, I have a pin over here, means I have a reaction both directions. I just have a vertical reaction, 4-foot modules, and I have different loadings. Let's see. Okay, so if I want to find members, let's say, so I want to find members, the forces in these members, EF, which is this horizontal member, JK, which is this member, and HJ, which is this member. If I was to do this by method of joints, it would take me a while to get there, right, from either side. I could start from here, I could go around, or I could start with this joint, but I got too many unknowns, so I'm going to need to bring in the reaction somehow. But in any event, in order to solve this, I need to find the reactions. So how do I find the reactions? If this is D, and this is A. How do I find reactions? These are our reactions, here, here, and here. Do I have anything in the horizontal direction? No. So that's 0, right? We don't care. So it's just what's happening at A, what's happening at D. So how do I do it? What's throwing you off looking at this? All the members? They don't care, right? I mean, even if this thing was a large plate, or a large beam, and I had all these forces on here, how would I solve the reactions for that? Yeah, just on the moments. So don't worry about all the truss members. Look at these forces. These are our external forces. And these are we're looking for the reactions. So these external forces are creating the reactions, right? They're also creating the force inside the members, but we'll get to that in a minute. The problem is asking for find the force in these members EF, JK, and HJ, but I still need these reactions. I need this and this. So how do I solve it?
Some of the forces in the line.
What?
Some of the forces in the line.
Around which?
In the line there.
Well, I can't sum forces. Well, you can sum forces in the y direction, but what's it going to give me? It's going to give me 2 unknowns. Then I'm going to need a moment equation.
So moments of the A.
So just do moments at one side or the other. I put my moments at A, I sum moments at A, gives me 1 unknown, right? Just like a beam problem. So sum the moments at A. So that you just have a bunch of forces you got to deal with. So how do I do it? What do I do with the 2 kip force? Spinning around A in this direction. So what is it?
Times 4.
2 kips times 4 feet. What else? What? plus 8 kips times what? 8 feet. What else?
Plus 5 kips times 12.
Plus 5 kips times 12 feet. What else? The 4 kips times what? Okay, what else? And we have 3 times 20. What else? What? Yeah. Minus D times 24. Okay, this is all equal to 0. So what is it? What's D? I think I did this right. 2 times 4, 3 times 18. Oops. I made a mistake. This is 3. Sorry. Trying to keep it whole numbers. If I can. What? 9. Okay. Now you can do your sum of the forces in the vertical or in the Y. So I have 9 minus what? 2 minus 3 minus 5 minus 4 minus 3 plus A. What's A? 8. Okay, these are our reactions. We have 9 kips and we have 8 kips. Okay? So, the problem at hand then is find these forces in these elements, in these members. So it's this one, it's JK, and it's JH. So I'm going to do a section cut right through here. Alright? I'm going to cut a section through that. And with that, I'm going to do a free body diagram of one side of this truss or the other. So let's do our free body diagram. Okay, so that's essentially a set and a cut, right? So all I did is I took this, just this section that we cut here, right, all of this, and I drew it with the forces exposed now, right? Okay. So the same way we did the other truss, how are we calculating this? What do we want to find first? Let's say we want to do EF. Let's do over here. EF, I need dimensions here, right? I need that this thing is 4 feet here, and then we have 4-foot modules, right? All 4-foot modules and 4 foot high, so dimensions are not that difficult to figure out. But if I want EF, what do I want to do? This is my node. I'll cut these forces. I want this. Remember, I'm looking for that. What can I do?
Some of the moments at J.
Some of the moments at J, okay. Good. Right, what happens? These two forces get isolated. I don't care about them anymore. And I'm just left with just an EF. So all I have, and this 5 kips goes away, so I'm just left with the 3 kip, the 2 kip, the reaction, and that 4. So that's it. I would do that. Some of the moments at J equal to 0. So what do I have? Let's start with the 8 kip force.
Minus.
Well, if I'm spinning this way, from here, you put yourself at that spot. So all these vectors go through you, and the 8 kip force is spinning this way. What? Positive. So I have 8 kips, and what's my distance? What?
12 feet.
12 feet. Okay. The 2 kip force? What?
Negative.
Negative. And its distance? 8 feet. Well, the 3 kip force?
4.
4. What else?
E.
EF,
Positive.
positive. Time? 4. Why 4? That's the perpendicular distance, right? So, equal to 0, EF. What do you get? What? What's the math? This is a 4. 4. Yeah. EF is equal to 17 kips. Is it compression or tension? Pulling, right? Yeah. So EF is going to be in tension, right? Is that right? Oh wait, it's negative, isn't it? It's negative 17 EF. So what happens? This is going the other way, right? It's going like that. So now EF is equal to 17 kips in compression. Okay, and that makes sense. When you pull on this truss, you pull from the bottom, right? What's happening? This is elongating, and this is going into a compression, right? So you can imagine when you pull down on this, you're pulling all this into tension, and you're throwing these forces at the top going into compression. So it does make some sense. All right,
No.
let's finish out. How do we get JK, which is this element? JK. Yeah, JK is this little. What? How do I do that? What? What's the angle of this element here? What? 45. What? How do you know it's 45 degrees?
It's 4 by 4.
4 by 4, right? This has got to be 2 by 2, bisecting this in the middle, 45 degrees, right? So, how do I solve for JK? I need the components, right? I need the components of JK. I need something like that, something like that. But I don't know anything else horizontal with this. I have all this that's vertical. So if I balance everything in the vertical direction, I could solve for that one force. So looking for JK, some of the forces in the vertical direction. How do I balance it? What's the 8 doing? Positive, negative? What? Positive, so it's 8 kips. The 2 kips is what? Negative. The 3 kips? The 5 kips? Okay, what's the vector then? JK what? Yeah, whatever, but it's a positive or negative? Based on that? Positive. Positive JK cosine 45, which is 707, right? This is equal to 0. Solve for JK. What? Yeah, 2.83 is what I got. And compression or tension? Tension, right? It's pulling away from this node. This is the direction of the force we drew, so it's pulling away, so it's in tension. It's a positive number, so that direction stays, and it goes into tension. So JK is in tension. And then the last one we're looking for is HJ, which is this horizontal one. JH here. So how do I do that?
Is it 0?
What?
Is it 0?
Is it 0? No. Why do you think it's 0? Well, you have the component of JK, you have JH, and then you have EF, right? So we want to balance that. So let's do that. Let's do some of the forces in the x direction. We're looking for JH. Okay? Some of the forces in the x direction give me what? We figured out what EF was, right? What is EF? It's 17 kicks. We figured out what JK is. It's 2.83. Okay? So, how do I need the component of JK again down here, but let's write the equation. Which way is JK going? If this is correct, JK is going positive. But what's it equal to? It's a component of that, right? So, what is it? It's JK sine 45 or cosine 45. Okay. What else? EF, it's going the other way. EF is 17. And what we're looking for, which is JH, right? So we're looking for JH. JK we know is 2.83. So plug it in. This is 0.707, right? So solve for JH. JH becomes 17 minus 2.83 times 707, 0.707. Yeah, 15. And is that tension, compression? It's pulling away from the node?
Tension.
Tension. Okay, so we solve for JH, we solve for our EF and JK. Right? So without going through all the joints, we were able to figure out what was happening here, here, and here. Right? You can do that anywhere else. So if I gave you a problem in an exam for a truss, and I want you to look at one particular member, that's what you can do, right? You can figure out what's going on, that force in that one particular member. So that's method of sections, right? So now you're experts in method of sections. Okay. So we need to practice this method of joints, method of sections, all right? And we're going to go over it in the seminar. So don't let it trip you up. It's really the same exact thing that we've been doing. Everything we're doing is equilibrium, and everything we're doing are three equations of statics. Some of the forces are vertical, some of the forces are horizontal, and then the moments, no matter what we're doing, right? So in the seminar, I want to go through what we're going to cover on the exam, the type of, not exactly the type of questions, but all the topics that we want to look at, all right? And just study all the notes, all the homeworks, all the things we did in class. That's what the test, that's what the midterm's on. It's not meant to trip you up, but you're not going to see a problem exactly like anyone that you've ever done before. It's going to be you applying what you know, right? So you're going to take what you've done and what you've done so far and all the way you've applied it, and you're going to do the same thing. You're going to think about how to apply it, all right?